Good evening to all. Good evening to all. I'm very happy to welcome you all for this TNSET exam preparation online coaching class. It's a wonderful platform to all the aspirants who are preparing for the TNSET examination 2024. And today, chief guest, it's an inspiring person, and also she cleared her TNSET examination in 2018. None other than the eminent person, Dr. S. Sweetha. She did her PhD from Bardiyar University and also published more than 8 papers in reputed international journal. It's our pleasure and proud moment to call upon our guest, Dr. S. Sweetha. I welcome you, ma'am.
Yes, ma'am. Thank you, ma'am. Thank you for your introduction.
The wonderful event was organized by Indian Mathematical Professor Association and Infinity Research and Development and also Bharatiyan Alumni Trust. Let's start our program. Ma'am, you can start your session, ma'am.
Okay, ma'am. Thank you. Thank you for the opportunity. I'll start now. Okay, good evening, all. Is my screen visible, ma'am?
Yes, ma'am, it's visible.
Okay, I'll start. Today we are going to see, yesterday we saw about vector spaces, subspaces, linear transformation. Today we are going to see about the algebra of matrices, matrix and different type of matrices and all the theory related to that. First, what is a matrix? Matrix is nothing but a M by n matrix is nothing but a rectangular array of mn numbers. It may be a real, complex, or any irrational, or any numbers arranged in an ordered set of horizontal lines called rows. These horizontal lines are called rows, and these vertical lines are called columns. This is an M by n matrix. Here M is not equal to n. So we can call this matrix as rectangular matrix. If M is equal to n, it will be a square matrix. Square matrix, 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix, and all that. It will be a square matrix. If the matrix has only one row and any number of columns, we can say this matrix is a row matrix. Row matrix of 3 columns. Row matrix means only one row will be there and any number of columns. A matrix is said to be a column matrix if it has any number of rows and exactly one column. Then this matrix will be a column matrix. If all the entries of the matrix is 0, then we can say it is a null matrix. Next, in square matrix, if it is a square matrix is said to be a diagonal matrix if elements except these diagonal elements, that is all the elements except these diagonal elements where I not equal to j. Here a, I, j. If I not equal to j, all the entries are 0 for I not equal to j. We can say it is a diagonal matrix. That is 2, 3, 5, 0, 0, 0. This is an example of diagonal matrix where we have only diagonal elements. It's said to be a scalar matrix for if it should be a diagonal matrix and all these diagonal elements should be equal. So 1, 1, 1 is a scalar matrix. Maybe 2, 2, 2 or any real or complex numbers. A matrix is to be a unit matrix or identity matrix if the diagonal element is exactly 1. If the diagonal elements are 1, then we can say this matrix is a identity matrix. And triangular matrices. A matrix is said to be a triangular matrix A matrix A is said to be a upper triangular matrix if it has entries in the diagonal and above the diagonal. If the matrix has entries in the diagonal and above the diagonal, then this matrix is an upper triangular matrix. For example, A equal to some 2, 3, 4, 5, 0, 4, 1, 0, 0, 2. Then this matrix is an upper triangular matrix. A matrix is said to be a lower triangular matrix if it has entries below the diagonal. So this is lower triangular matrix. A matrix is said to be a tri-diagonal matrix if it has entries in the principal diagonal. A tri-diagonal matrix is a matrix if it has entries, non-zero entries in the principal diagonal, super diagonal and subdiagonal. That is, it should have values 2, 4, 2, 3 in the diagonal and super diagonal. Super diagonal is 5, 6, 1. This is super diagonal and all other entries are 0. And subdiagonal 5, 6, 1. And all other entries are 0. So this matrix, if it has non-zero entries in the diagonal, super diagonal and subdiagonal, then this matrix is said to be a tri-diagonal matrix. Next, equality of two matrices. A matrix A and matrix B is said to be equal if it has same number of rows. If M is equal to P and N is equal to Q, if it is of order same, that is same number of rows and columns, and all the entries of A should match with all the entries of B. A matrix A 1, 0, 2, 3 is said to be equal to a matrix B. If this is of order 2 by 2, then B should be of order 2 by 2 and all the entries must be same. So we can say that a matrix A is equal to B. Addition of two matrices. Addition of two matrices means we have to add the corresponding entries 1 plus 1, 2 corresponding entries of these two matrices. 0 plus 0 is 0, 2 plus 2 is 4, 3 plus 3 is 6. So addition of two matrices is nothing but addition of corresponding elements of elements, and addition of a matrix is possible only if it is of same order. There are some properties for addition of two matrices. Here addition of two matrices satisfies the commutative property A plus B equal to B plus A. You can solve you can try it with any examples. And associativity, it also satisfies associativity. A plus B plus C is equal to A plus B plus C. And for a matrix of order, for a matrix O of order m by n, that is order same as of A, which satisfies this equation, that is A plus O is equal to O plus A equal to A. If it satisfies this equation, then O is said to be the additive identity. And then for any matrix A, if there exists a matrix minus A, such that A plus minus A will be the additive identity element of the matrix. So additive inverse also exists. Hence this forms a group. Scalar multiplication. A matrix is for a matrix A equal to A, B, C, D. Scalar we can multiply a scalar so that this scalar will multiply to all the elements. So we will get lambda A, lambda B, lambda C, lambda D. So scalar multiplication will be of the form like this, and these are some of the properties. Here lambda of A plus B is equal to lambda of A plus lambda of B. This satisfies for lambda of A minus B also. And for any scalars lambda and mu, we have this property, distributive property. And for lambda u scalars, the scalar multiplication also is possible. for minus lambda, that is for any additive inverse of the scalar, this condition is also satisfied, and unit element is also 1 into a is nothing but a, minus 1 into a is minus a. Matrix multiplication, we all know that for a matrix multiplication, a matrix A and B, AB is possible if the number of columns is equal to the number of columns of A is equal to the number of rows of B. If A is of order m by n, B should be of order n by some P. So if the number of columns of A is equal to number of rows of B, then the matrix multiplication is defined. For example, A is 1, 2, 0, 4. Here number of columns of A is 2. Hence B must be of order. B must have 2 rows. 4, 1, 2, 3, 0, 0. So number of columns of A matches with the number of rows of B. Hence AB is defined. AB multiplication is possible if this row is multiplied with the corresponding column. So 1 into 4 is 4 plus 3 into 6 6, and first row with second column 1, 1 into 1 1 plus 2 into 0 is 0. First row with third column will take the form 1 into 2 is 2 plus 2 into 0 0, and second row with first column 4 3s are 12, second row with second column 0, second row with third column 0. Hence the AB is of order 2 by 3, that is 2 by 3. If AB is defined, BA is not necessarily BA is defined, because B is of order 2 by 3, A is of order 2 by 2. Here matrix multiplication is not possible. If AB is defined, BA may not be defined. Even if AB and BA are both defined, that is, if both are square matrices, still A and B may be of different orders. For example, if A is 3 by 4 and B is 4 by 3, AB will be 3 by 3 and BA will be 4 by 4. If AB and BA are both defined and are of same orders, in the case of square matrices, AB and BA may not be equal. Example, matrix A, here matrix B, AB is defined and is of order 2 by 2 and BA is of order 2 by 2. Here AB is not equal to BA. So, it does not, matrix multiplication is not commutative. Here A square is nothing but A into A when A is a square matrix. That is, if A should be a square matrix, then only A square is defined. If AB is, if in general for any scalar, if x into y is equal to 0, we can say either x is 0 or y is 0. But in the case of matrices, this is not possible. Here, for example, A is a non-zero matrix, B is a non-zero matrix, but AB is a zero matrix and BA is also a null matrix. So, if AB is null matrix, it does not imply A is 0 or B is 0. If AB is a null matrix, then BA is cannot BA is not necessarily be a null matrix. For example, this is AB. Here AB is a 0 matrix, but BA is not a 0 matrix. So, this is also not possible. If AB equal to AC, we cannot cancel like this. This does not imply B is equal to C. For example, A is a matrix, B is this matrix, C is this matrix. AB by matrix multiplication we will get like this, and AC will get like this. This does not mean that B is equal to C. Here AB is equal to AC, which does not mean B is not here, B is not equal to C. The properties of matrices. Associativity under multiplication is defined for matrices. AB into C is equal to A into BC, and distributivity over addition is also satisfied. If A is a matrix of order m by n, Then we can multiply identity matrix of order m, and we will get the same matrix A. We can multiply, we can pre-multiply, and also we can post-multiply. In both cases, we will get the same matrix A. If A is a m by n matrix and O is a null matrix, that is zero matrix, and then A into null matrix is nothing but a null matrix, and null matrix into A is nothing but a null matrix. If matrix multiplication is defined, this condition satisfies. For a square matrix A power m into A power n is equal to A power m plus n. That is, if A square into A cube is nothing but A power 5. And A square into A cube is nothing but A power 6. So A power m whole power n is nothing but A power mn for all mn. Transpose of a matrix. Transpose of a matrix means if this is a matrix A, B, C, D, and A transpose is nothing but interchanging of rows and columns. Here we are taking this row and writing it as a column. The next row, second row as second column, third row as second and third column. This also holds for a rectangular matrix A, B, C, D. Here let us take E, F. So this is a 2 by 3 matrix, and A transpose will be A, B, E, C, D, F. It will be a 3 by 2 matrix. So A transpose of whole transpose is nothing but the same matrix A. And the lambda of A transpose is equal to lambda A transpose. We can take the scalar outside, and we can say that lambda A whole transpose is equal to lambda A transpose. Here they have represented transpose like this. And A plus B transpose is equal to A transpose plus B transpose. This condition is important. A plus B transpose is equal to A transpose plus B transpose. Here AB in multiplication, AB the whole transpose is nothing but B transpose A transpose. In the case of three matrices, A, B, C whole transpose is equal to, we can write this as AB, C transpose into AB transpose. Again, we can write it as C transpose, B transpose, A transpose. This is called reversal law. And conjugate of a matrix. If the matrix has complex entries, that is, if the matrix is 1 plus I minus I 2 plus 3I. A bar, A conjugate matrix. A bar is nothing but replacing this conjugate element. That is 1 plus I conjugate is 1 minus I. Minus I conjugate is plus I. 2, it is a real number, so it takes the same value as 2 plus 3I is nothing but 2 minus 3I. So A conjugate, A bar is nothing but A conjugate. Here the properties of A conjugate is A bar transpose is nothing but that is, we can represent A bar the whole transpose by A theta in this papers, in this upcoming topics. Here A conjugate, the whole conjugate is nothing but the same matrix. Again, by applying conjugate, we will get this, applying conjugate to A bar, we will get 1 plus I minus I 2 plus 3I, which is nothing but the same matrix. And A plus B, the whole conjugate is nothing but A bar plus B bar. And lambda A, the whole bar is equal to lambda bar A bar. Here, if lambda is real, it will be lambda bar is equal to lambda. If it is complex, its conjugate, it will be a conjugate of lambda. AB, the whole bar is nothing but A bar B bar. Conjugate is different from transpose. Here AB, the whole transpose is B transpose A transpose. In the case of conjugate, AB the whole bar is A bar into B bar. A conjugate of conjugate is nothing but A. That is conjugate transpose of conjugate transpose is nothing but a plus b of theta is a theta plus b theta, and lambda a of theta is lambda bar a theta, ab the whole theta is b theta a theta. Here transpose is applied, so ab theta is nothing but b theta a theta, whereas in the conjugate ab the whole bar is a bar b bar. And types of matrices. If a matrix is a square matrix is called an idempotent matrix, then we can say if a square is equal to a, then the matrix A is called an idempotent matrix. Let us check whether I minus in. If A is of order n by n, in minus A is idempotent or not. In order to prove prove in is idempotent. So to prove in minus a the whole square is nothing but in minus a square is equal to a. So in minus a the whole square is nothing but in square is identity matrix square is identity matrix minus a plus a square. Here, if A is an idempotent matrix, prove in minus A is idempotent. Since A is an idempotent matrix, we can write A square is equal to A. So minus A plus A cancel. So we will get in minus A. So if A is an idempotent matrix, in minus A is also an idempotent matrix. Another condition, if AB is equal to A and BA is equal to B, if these two conditions are satisfied, then both A and B are idempotent. Proof, if AB is, let us take AB is equal to A. Multiply A, post multiply A on both sides. A, B, A is equal to A into A. A into A is here BA is nothing but B. BA is B. So AB is equal to A into A is A square. Here AB is again AB is equal to A. So AB is equal to A, which is nothing but A. So A is an idempotent matrix. Whereas we can prove this for B is idempotent also. Here BA is equal to B. Post multiply with B, we'll get B square. AB is nothing but A, BA equal to B square. Again BA is nothing but B, so B square equal to B. So hence the matrix A and B are idempotent. If AB equal to A and BA equal to B, then we can say that A and B are idempotent. Please remember these matrices name. Idempotent means A square equal to A. Example, this is an idempotent matrix. Check this example, take this as exercise. Periodic, a matrix is said to be periodic if a power k plus 1 is equal to A, then the matrix is said to be of a period k. If A square is equal to A, we can say A is of period 1. If A cube equal to A, then A is a matrix of period 2. Next, nilpotent. A matrix is said to be a nilpotent matrix if A power k is a zero matrix. Then the matrix A is said to be nilpotent of order of index k. Here the matrix B is said to be nilpotent of index 3. Here B square will get one matrix, then B cube we will get as 0 matrix. So B is a nilpotent matrix of order of index 3. Involutory matrix. If A square is equal to I, then the matrix is said to be involutory. Here we know that I square is equal to I. So I is itself an involutory matrix. Here, check this example. C square is equal to, multiplying this, we'll get a C square is equal to I. This is an involutory matrix. Next, symmetric and skew symmetric matrices. A square matrix A is said to be symmetric if A is equal to A transpose. That is, if A, B, C is given, D, A11, A12, A13, A22, A33. Symmetric means A is equal to A transpose. When a matrix is said to be when a matrix is said to be equal to its transpose, when the elements, when the rows and columns are equal. So A21, A31, when A12 is equal to A21 and A13 is equal to A31 and A23 is equal to A32, then the matrix is said to be a symmetric matrix. The diagonal elements can be anything, but the corresponding Aij and Aji should be equal. So this matrix is said to be a symmetric matrix. Skew symmetric matrix. If A is equal to minus A transpose, or in other words, A transpose equal to minus A. If the matrix A satisfies this condition, then it will be a skew symmetric matrix. For example, let us take A, B, C, D. A matrix A is equal to A minus A transpose is nothing but minus A, minus C, minus B, and D. Here A is equal to A, B, C, D. A transpose is nothing but A, B, C, D. Skew symmetric means A transpose equal to minus A. So minus A is nothing but A transpose is A, C, B, D is equal to minus A, minus B, minus C, minus D. So equate the corresponding elements. A is equal to minus A, C equal to minus B, B equal to minus C, D equal to minus D. Bringing this both sides, 2A is equal to 0, which implies A is 0. And bringing this D here, 2D is equal to 0, which implies D is equal to 0. And C is equal to minus B. That is, the diagonal element should be 0. If B is here, C is nothing but minus B. So, skew symmetric matrix, the diagonal elements will all be 0 and the corresponding Aij is nothing but minus of Aj. If 1 is here, in the corresponding column, there will be minus 1, 2, minus 2, 3, minus 3. All the diagonal elements, diagonal entries of the skew symmetric matrix is 0. And properties of symmetric and skew symmetric matrices. These properties are important because there will be at least one question from this section. Symmetric, skew symmetric, Hermitian, skew Hermitian. A matrix, for a matrix, square matrix A plus A transpose is a symmetric matrix. And A minus A transpose is nothing but a skew symmetric matrix. A into A transpose and A transpose into A are symmetric matrices. Let us take one condition. Let us take, in order to prove something, you should take general form. In order to prove it is false, you can take examples. Here we are going to take, we are going to prove A plus A transpose is symmetric. A matrix A is said to be symmetric if A equal to A transpose. Here A plus A transpose, we need to prove A plus A transpose is symmetric. In order to prove that, we need to take A plus A transpose, the whole transpose is nothing but A plus A transpose. Here A plus A transpose, the whole transpose, A plus B, the whole transpose is equal to A transpose plus A transpose, the whole transpose. Here A transpose of transpose is nothing but the same matrix A. So we can write like this. So A plus A transpose the whole transpose is equal to A plus A transpose. Then the matrix A plus A transpose is symmetric. In the same way, we can prove that A minus A transpose is a skew symmetric matrix, and A into A transpose plus and A transpose into A are symmetric matrices. And the diagonal elements of a skew symmetrics are always 0. For a skew symmetric matrix, the diagonal elements will be 0. Every square matrix A can be written as sum of symmetric and skew symmetric matrix. This is one of the important property. Any square matrix A can be written as a sum of symmetric plus skew symmetric matrix. So the symmetric matrix will be of the form A plus A transpose by 2. Skew symmetric is nothing but A minus A transpose by 2. So A plus, we know that A plus A transpose is symmetric matrix, and we are multiplying the scalar by 1 by 2. And we also know that A minus A transpose is a skew symmetric matrix. We are multiplying the scalars by 1 into 1 by 2. By adding this, we will get A by 2 plus A by 2, which is nothing but A. So any square matrix can be uniquely written as a sum of symmetric plus skew symmetric matrix. So symmetric matrix means A plus A transpose is symmetric. We know that from this property. Here A minus A transpose is skew symmetric from this property. If A and B are symmetric matrices of same order, then AB is symmetric. If A is of order 2 by 2 and B is of also 2 by 2, then AB is also a, if AB is symmetric, then AB is equal to BA. Let us take this condition. Here, if A and B are given, A and B are symmetric matrices. Let us assume AB is symmetric. If AB is symmetric, we can say AB the whole A transpose is nothing but AB is symmetric, AB the whole transpose is equal to AB. Here AB the whole transpose we can write we can write AB the whole transpose as B transpose A transpose is equal to AB. We know that B is a symmetric matrix, so B transpose is equal to B, and A is a symmetric matrix, so A transpose is equal to A, so BA is equal to AB. And this is why if AB is equal to BA, and we can take transpose on both sides, and we can get this condition. So if A and B are symmetric matrices, if AB is symmetric, we can say that AB is equal to BA. That is the commutation between A and B is satisfied. That is A and B commute. Next, B transpose AB is symmetric or skew symmetric according as A is symmetric or skew symmetric. If A is symmetric, any matrix B transpose AB is symmetric. If A is skew symmetric, any matrix for any matrix B transpose AB is skew symmetric. And all integral powers of symmetric matrix are symmetric. That is, all powers of symmetric matrix is again a symmetric matrix. And Hermitian and skew Hermitian. This is same in the case of symmetric and skew symmetric, but here we have complex entries. Here a matrix A is said to be a Hermitian matrix if A is equal to A bar transpose. A bar is nothing but conjugate and its transpose. If A is equal to A bar transpose, then the matrix is said to be a Hermitian matrix. For example, let us take A is equal to 1 plus 2i, 0, 1 minus I, a matrix A is said to be Hermitian if A is equal to A bar transpose. That is, if A is a matrix, so its transpose should be equal. So diagonal elements will always be real entries. It is 2, 3, 1 plus I. Here 1 minus I. Here conjugate will be like this. So if here for a Hermitian matrix, all the diagonal entries will be real, and the corresponding row and column vectors will be conjugates. If if A12 is 1 minus 2i, A2i will be 1 plus 2i. If A13 is 4 plus 7a, A31 will be 4 minus 7i. So this matrix is said to be Hermitian. A matrix is said to be skew Hermitian if A is nothing but minus of A bar transpose. So here all the diagonal entries will be purely imaginary numbers. Here all the diagonal entries will be real numbers, purely real. Here all the diagonal entries will be purely imaginary. So that we can get if A11 should be is equal to A bar 11 should be equal to A11. Sorry, minus A11. So 5i will be equal to minus, if A11 is 5i, A bar 11 is minus 5i, and minus A11 is 5i. So these diagonal entries will should be purely imaginary numbers, and um, all the in all the other corresponding elements, the sign of real numbers will vary. The sign of real numbers will vary. Whereas in the case of Hermitian, it will be a conjugate. The sign of imaginary numbers will be opposite. Here, the sign of real numbers is different. So, all the diagonal elements of skew Hermitian are either 0 or purely imaginary. If 0 is there, then the condition will satisfy. Then, orthogonal matrix. A matrix A is said to be an orthogonal matrix if A into A transpose is equal to I, and A transpose A is equal to I. If this condition is satisfied, that is A transpose equal to A transpose A is equal to I, then the matrix is said to be an orthogonal matrix. Here if we multiply this with this A transpose, we will get the identity matrix 1 0 0 0 1 0 0 0 1, and the conditions of orthogonal matrix. Since A into A transpose is equal to I, determinant of A transpose is nothing but determinant of I. That is A transpose is equal to I, which is nothing but determinant of I, which is nothing but 1, which is not equal to 0. Hence, here we can write as A. The properties of determinants we will see later. Here, note that every orthogonal matrix is non-singular and every orthogonal matrix is invertible. That is, inverse exists for every orthogonal matrix. If A is orthogonal, A transpose and A inverse is also orthogonal. A transpose is equal to I, A transpose A is equal to I. Here A inverse equal to A inverse A is I. Inverse condition. Here A transpose is nothing but A inverse. That is, every orthogonal matrix has an inverse invertible matrix. That is, every orthogonal matrix is invertible. If A is orthogonal, A inverse is also orthogonal and A transpose is also orthogonal from this condition. If A and B are orthogonal matrix, and AB and AB and BA are also orthogonal. There are proofs for this, but remember the properties alone. Determinant of an orthogonal matrix is nothing but plus or minus 1. Here the determinant of matrix identity matrices will be plus or minus 1 depending upon the sign and order of the and the nature of the matrix. So determinant of an orthogonal matrix is always plus or minus 1. This is one of the important properties. Please take note of it. If A is an orthogonal matrix with determinant of A is 1, A is said to be a proper orthogonal matrix. If A is orthogonal matrix with the determinant is minus 1, it will be an improper. We can say it as an improper orthogonal matrix. In the real for real numbers, we are saying A into A transpose equal to A transpose A equal to I as orthogonal matrix. This is same in the case of conjugate transpose A bar transpose A into A bar transpose equal to A bar transpose A bar transpose A is equal to I. Then we can say this matrix A is said to be an unitary matrix. For example, this is a unitary matrix. Here A into its conjugate transpose will be an identity matrix. And determinant of unitary matrix will be of modulus unit. And if A is a unitary matrix, the same A bar, A transpose A bar, A conjugate transpose A inverse are all unitary. Product of two unitary matrices is always unitary matrix. A square matrix is unitary if and only if its columns form an orthogonal set of vectors. We will see this in tomorrow's or day after tomorrow's class, what is orthogonal and orthonormal set and all. And if A is Hermitian and P is unitary, we can say that AP inverse AP is Hermitian. A is a Hermitian matrix, and if P is a unitary matrix, we can say P inverse AP is a Hermitian matrix. Next, permutation matrices. This we will see in the algebra class because we need to know about symmetric group and all that. Here, just take a note of its definition. Permutation matrix is any n by n matrix which can be created by rearranging the rows or columns of the n by n identity matrix. Here, these are for order 2 by 2, the permutation matrices are 1 0 0 1 and 0 1 1 0. Next, determinant. So, how do we find the determinant of a matrix? We denote determinant of A as like this. For example, let us take A is equal to A, B, C, D. Determinant of A is nothing but multiplying. This is determinant for 2 by 2 matrix. Multiplying this principal diagonal elements and subtracting the non-diagonal AD minus BC. This AD minus BC, which is given here A11 A11 into A12 minus A21 into A12. For a 3 by 3 matrix, we are taking A11 into this minor. For A11, excluding this row and excluding this column, we are taking the determinant of 2 by 2 matrix and minus A12. Here this is positive. First element A11 will be positive and here A12 will be negative and A13 will be positive. Minus A12 into excluding this row and column, we get A21 determinant of A21, A23, A31 and A33. And again plus A13 into A13 into excluding this rows and column, a determinant of A21, A22, A31 and A22. Likewise, it goes on for 4 by 4 matrices, 5 by 5 matrices, 6 by 6 matrices. Let us see an example for determinant of a 3 by 3 matrix. A is equal to 2, 3, 4, 5, 0, 1, 0, 1, 2. So, determinant of A is nothing but plus 2 into determinant of 0, 1, 1, 2. Which is nothing but 0 minus 1 and minus 3 into excluding this row, we have 5, 1, 0, 2, which is nothing but 10. plus 4 into excluding the row and column like this, we get 5001 plus 4 into 5 minus 0 is 5 minus 2 minus 30 plus 20, so minus 8. So determinant is determinant of a 3 by 3 matrix A is nothing but minus 8. Determinant of an identity matrix, that is a unit matrix, is 1 0 0. Let us take it is of order 3 by 3 0 0 1. Determinant of I is nothing but 1 into 1 and minus 0 plus 0. So determinant of an identity matrix is 1. Determinant of a 0 matrix is 0. And if A is a n by n matrix, then the matrix obtained from A after deleting ith row and jth column is called submatrix. If this is A is this matrix, if I am deleting the first row, first column and the third row, then I will get 3 4 0 1. This is a submatrix of A. If I am deleting second row, if I am deleting second row and second column, I will get the matrix 2 4 0 2. It is a submatrix. So if any matrix deleting ith row and jth column, we will get the submatrix. Only square matrix have determinants. So square only we can able to find the determinant only for a square matrix. Determinant of a square matrix can be evaluated by expanding from any row or column. It is need not necessary that we have to multiply from the first row. If we can take A21, A22 and A23 also, whereas the signs will be here, it will be A for A11 it will be plus, A12 it will be minus, plus, and again it is minus, plus, minus, plus, minus, plus. So if minus A21 into its corresponding by deleting the first row and the second first column and second row, A12, A13, A32, A33, and plus A22 into the corresponding determinant minus A23. We can obtain the determinant using any row or any column. Here we have taken first row only. Sum of product of element of row with their corresponding cofactors is equal to value of determinant. This is called the cofactor. So product of a row with its corresponding cofactor is nothing but the determinant, which they have given like this. Sum of product of element of row with the cofactor of element of some other row is 0. If I am multiplying A11 with another cofactor matrix, and its sum will always be 0. And value of a determinant remains unchanged if its rows and columns are interchanged. If row and columns are interchanged, then the value of a determinant will be the same. That is determinant of A is equal to determinant of A transpose. If two adjacent rows or two adjacent columns of a determinant are interchanged, the determinant remains its absolute value but changes its sign. For example, here let us shift the first row and the second row. 5 0 1 2 3 4 0 1 2, and determinant of this matrix will be 8, because if we are changing one row and another row, we have to multiply by minus, and if we are changing again, we are changing second row and third row, again we have to multiply by minus. So minus into minus will become plus. If we are making any one change, we have to multiply with minus sign. So determinant of, let us take this determinant. Determinant of A is nothing but 5 into 3 2s are 6 minus 4 minus 0 into what? We don't need to compute this because 0 into anything will be 0, plus 1 into 2 minus 0. 10, sorry, minus 10, here the by changing its sign it will be one minute. I'll just refer this and will say you, but the absolute value remains changed, only the sign changes. I'll just give another example for this. By switching any two adjacent rows, sorry, we have to interchange the columns also. We are interchanging the columns, that is A is equal to 5 if we are interchanging the columns like this, and we'll get the same absolute value, that is the matrix determinant will be same, but its sign will be different based on which row and which columns, how many rows and how many columns are changed. If any line of determinant A is passed over R parallel lines, then the value of new determinant will be minus 1 to the power R. If it passes over two parallel lines, it will be the same, determinant will be the same. If all the elements of any two rows or two columns of a determinant are either identical or proportional, then determinant is 0. If 1 1 1 1 1 1 and 2 3 4, then we'll get the determinant of this matrix will be 0. If 1 2 2 4, the value of the determinant is also is 0. If each element of a row or column is multiplied by the same number k, then the determinant is multiplied by k. If every element is multiplied by k, and the whole determinant is multiplied by k. If A is a square matrix of order n, determinant of k is nothing but k power n into determinant of A, where k is any scalar. Here if each element of row or column consists of R terms, then the determinant can be expressed as sum of R determinants. And another property, if A and B are square matrices, this is an important property. Determinant of AB is equal to determinant of A into determinant of B. And determinant of A square is nothing but determinant of A the whole square. This is an important property. Please take note of it. Next, if delta is the determinant of order n, delta transpose is the determinant obtained from delta by replacing the elements by the corresponding cofactors. Determinant of a skew symmetric matrix of odd order is always 0. Let us take skew symmetric matrix to be 0, since the diagonal elements are 0, 2 minus 2, 1 minus 1, 3 minus 3. Let us assume the matrix, this is a skew symmetric matrix. We can, in order to prove, we have to take general form. So let us take as 0, 0, 0, A12, A13 minus A12, A23 minus A13 minus A23. By finding the determinant, minus A0 into something minus A12 into 0 minus of 0 minus A13 into A. into A23 plus A13 into A12 into A23 minus 0. It is A12, A13, A23. It is plus A13, A12, A23, which is nothing but 0. So, determinant of a skew symmetric of odd order is always 0. If we take of even order, A12 minus A12, 0, then its determinant is 0 minus of minus plus A12 square. So determinant of a skew symmetric matrix is of odd order is always 0. If all the elements of row of a determinant are 0, then the determinant is 0. If all the elements of determinant above or below the main diagonal, if it is any upper triangular or lower triangular matrix, then the determinant will be product of the diagonal elements. Determinant of a diagonal matrix is nothing but the product of diagonal matrix. If this 2, 3, 4 is a diagonal matrix, by calculating this 2 into 3 into 4, 12. So the product of the diagonal elements is nothing but the determinant. Conjugate of a determinant. Conjugate of, we represent the conjugate of a determinant like this. And if determinant becomes 0, if x equal to a, then x minus a is a factor of a determinant. A square matrix is said to be singular if determinant is equal to 0. A square matrix is non-singular if determinant of a is not equal to 0. And a plus determinant of a plus b is not equal to determinant of a plus determinant of ab. Whereas determinant of ab is nothing but product is same. Determinant of AB is equal to determinant of A into determinant of B, whereas determinant of A plus B is not equal to determinant of A plus determinant of B. These are some of the important operations on determinants. Here, we have to find the determinant of 1A square, 1B square, 1C square. Here, we are subtracting first row R1, we are R1 minus R2 and writing it in the first row. 1 minus 1 is 0, A minus B, A square minus B square. Here R2 minus R3 and we are writing it in the second row. 1 minus 1 is 0, B minus C is B minus C, B square minus C square, and third row we are keeping as such 1C C square. Here finding the determinant, we are removing a minus b. In this, from this determinant, I am taking a minus b from the first row and b minus c from the second row, and I will get 0, 1, a minus b, a square minus b square is nothing but a minus b into a plus b. From the second row I am taking b minus c, so 0, 1, and I'll have remaining b plus c and 1c c square. Finding the determinant, I am taking this first column plus minus plus, so 1 into its corresponding b plus c minus a minus b. So the determinant will be a minus b, b minus c and c minus a. This is the determinant value of this matrix. If the matrix is 1 omega omega square, and if this matrix is like this, we can find the determinant by first we are adding all the C1 is, we are making C1 to be C1 plus C2 plus C3, adding this 1 plus omega square, and here 1 plus omega square, here also omega square plus 1 plus omega, and in the second column and third column we are making it unchanged. We know that in complex numbers 1 plus omega square cube root of unity, which is equal to 0. So by substituting the values, if any row or any column of a matrix is 0, its determinant will be 0. See, here we consider the determinant of this skew symmetric matrix. Here taking the minus sign from the first row, second row and third row, we will obtain like this, and and taking its transpose minus, we'll get the value as minus delta. So delta is the determinant of A is nothing but A is equal to minus A. So determinant of A plus A is equal to 0. So A is equal to 0. Multiplying or dividing a number by k. Here in this determinant, we can divide this dividing by 1 by a. That is, here we are multiplying by 1 by a. So 1 by a, in first row we are multiplying a, and here outside we are making division 1 by a. In second row we are multiplying b, and outside we are dividing it by b. In third row we are multiplying by c, and outside we are dividing by c. And in here we are removing the ABC, ABC. We are dividing ABC from the third column and multiplying here. So we can say the determinant of this is nothing but this matrix, which is nothing but 1, which is of the form like this. So making sum of elements in a row. So here in the first column, I am adding all the columns C1 plus C2 plus C3 and writing the 2 plus 1 plus x plus 3 is x plus 6, 2 plus x plus 1 plus 3 is x plus 6, and 2 plus 1 plus 3 plus 6 is x plus 6, and balance 2 columns I am keeping it as same, and I am removing x plus 6 outside from the first column. So I will get 1, 1, 1, and it is easy to find the determinant here. Now let us find the determinant of this matrix, which is same as this. We have already seen one, instead of ABC they have given us x, y, z. Here determinant of 1x x cube. I am replacing first row. R1 is nothing by R1 replacing by R1 minus R2. 1 minus 1 is 0. X minus y, x cube minus y cube, and in second row minus third row 0, y minus z, y cube minus z cube, 1 z cube, which is equal to, I am removing x minus y from the first row. So I will get 0, 1. We can write x cube minus y cube is equal to x minus y into x square plus y square plus xy. X square plus y square plus xy. From the second row I am taking out y minus x, 0, 1, y square plus z square plus yz, 1 z cube. So finding the determinant of this 1 into y square plus z square plus yz minus x square plus y square, so x square minus y square minus xy, y square cancel. So z square minus x square plus yz minus xy. Z square minus x square I am writing it as z plus x into z minus x, and I am taking y out common from these two terms, z minus x. So I will get I am taking z minus x common, and I will get x plus y plus z. So the determinant of the matrix is x minus y into y minus z into x minus y into y minus z into z minus x into x plus y plus z. And determinant of this matrix. One x square x cube, 1 y square y cube, 1 z square z cube. So first row minus second row, 1 minus 1 0, x square minus y square, x cube minus y cube, second row minus third row, 1 minus 1 0, y square minus z square, y cube minus z cube, 1 z square z cube. From the first row, I am taking out x minus y. So 0, x plus y, x square plus y square plus xy. Here in second row, y minus z I am taking outside. 0, y plus z, y square plus z square plus yz, 1, z square, z cube. Taking the determinant of this, I will get x minus y, y minus z into x plus y into y square plus z square plus yz minus y plus z into x square plus y square plus xy. Multiplying this xy square plus y cube plus xz square plus yz square plus xyz plus y square z minus yx square minus y cube minus xy square sorry minus zx square minus zy square minus xyz minus xyz plus xyz y cube minus x cube minus xy square plus xy square and balance terms xz square minus zx square. I am taking x outside, zx outside, so I will get z minus x, and from this term y square z minus yx square, I am taking y outside. I'll have I'm taking y outside, so z from I'm taking 1 minute. Here zy square and plus zy square and my y square z minus y square z get cancelled. From these two, I am taking from this two, I am taking y outside. So z square minus x square I will get. I am taking z minus x as common. So I will get xz plus y into z plus x. So which is nothing but x minus y, y minus z, z minus x, xy plus yz plus zx. We obtain this determinant. Here compute the determinant like this: a into bc minus a square minus b into b square minus ca plus c into b a minus c square. So we'll get a cube minus a cube minus b cube minus abc plus abc plus abc 3abc. For this same as this same like this matrix, substitute this and find the determinant. So adjoint of a square matrix. Adjoint of a square matrix is nothing but transpose of the matrix obtained from replacing its each element from cofactor. That is, if A, B, C, these are some other elements. So if the cofactor of A will be a matrix, instead of A, I am writing the cofactor of A. Instead of B, I am writing its cofactor. And instead of C, I am writing its cofactor. And like this, if we take the transpose of this matrix, I will get the adjoint of A. For example, if A is equal to 2, 3, 4, 5, and cofactor of A is nothing but cofactor of A is Cofactor of 2 is 5. Cofactor of 3 is plus minus 4. Cofactor of 4 is minus 3. Cofactor of 5 is 2. Adjoint is nothing but adjoint of A is cofactor transpose. So 5 minus 4 minus 3 2. So this is the adjoint of A. If A is a square matrix, then A into adjoint of A is equal to adjoint of A into A is nothing but determinant of A into identity matrix. Determinant of A is 0, then A into adjoint A will be a 0 matrix. If adjoint A is equal to determinant of A power n minus 1 if determinant of A is non-zero. Adjoint of A is determinant of A power n minus 2. You can prove all these properties. Determinant of adjoint of A is nothing but determinant of A whole power n minus 1 the whole square. Adjoint of AB is nothing but adjoint of B into adjoint of A. Adjoint of KA is K power n minus 1 into adjoint of A. Inverse of a square matrix. So we can say if AB equal to BA is equal to I, then B is the inverse of the B matrix is said to be the inverse of A. So we can write B is equal to A inverse. It is if A is equal A into A inverse is equal to I. And inverse of the inverse matrix is nothing but the same matrix. A inverse the whole inverse is equal to A. And every square matrix does not have inverse. Sometimes because A inverse is defined by 1 by determinant of A into adjoint of A. If determinant of A is equal to 0, then this matrix A matrix does not have any inverse. If a square matrix has inverse, then determinant of A should be not equal to 0. If determinant of A is non-singular, then A is invertible. Inverse of a square matrix A will be a unique one. If A is non-singular, determinant of A is not equal to 0, then AB equal to AC implies B equal to C. In general, this condition does not satisfy. If A is non-singular matrix, if its determinant is non-zero, then this condition is satisfied. Reversal law. If A, B, C are invertible, A, B the whole inverse equal to B inverse, A inverse, and A, B, C the whole inverse equal to C inverse, B inverse, A inverse. If A is an invertible matrix and A transpose is also invertible, that is A transpose inverse is nothing but A inverse transpose. If A is a non-singular matrix, then determinant of A inverse is nothing but determinant of A inverse. That is A inverse determinant is 1 by determinant of A. Differentiation and integration of determinants. Here this is the delta of x is this matrix. So d by dx of del x is differentiating the first row and keeping the second and third row as common, plus differentiating the second row and keeping first and third row as same, plus determinating the third row and keeping first and second row as same. So this is how we differentiated differentiate the determinants. And the integration is also like the same. Instead of determinant, we are putting a integration symbol. If it has if any row is of real entries, if it is not a function, then it will be then its derivative will be 0. So it's d by dx of del x is nothing but a11 dash of x, a12 dash of x, a13 dash of x, and all other two rows are same. Elementary transformations. In general, a matrix if A is any m by n matrix 2 4 3 4 3 2 1 1 0 if any matrix, we can interchange. It is possible that it is possible to interchange any two row. We can interchange A1 and row 1, R1 and R2, and it is possible to interchange any two columns. And also, multiplying all elements of a matrix, we can multiply it by a non-zero scalar. And we can also, if it is possible, if we can multiply it by a scalar, and also we can add it with another scalar multiplied row. So elementary transformations are possible. So we are going to see the row reduced echelon form. Let us take an example. A is equal to 1 0 1 3 4 5 2 3 4. First, let us let us take an example for A inverse, and let us find the inverse of A. For this matrix, let us find the inverse. For that, cofactor of A. First cofactor of A, we have to find the adjoint. First cofactor of A. In the place of 1, we are getting 4 4 16 minus 15 is 1. In this place, I am minus sign because 1 2 place, and eliminating on this column 4 minus 12 minus 10 is 2, and here plus 3 3s are 9 minus 8 is nothing but 1. A minus, eliminating this row, 0 minus 3, minus of minus 3 is plus 3, and 2 is 2, here minus 3, here minus 4, 5 minus 3 is 2, in this place I am putting minus 2, here. This is the cofactor matrix. Adjoint of A matrix is its transpose 1 minus 2 1, 3 2 minus 3 minus 4 minus 2 4. Here 1 by determinant of A into adjoint of A. Determinant of A, I am finding the determinant 1 into 4 4 16 minus 15 is 1, minus 0 into any matrix, plus 1 into 9 minus 8 is 1. So 1 plus 1 is 2. Determinant of A is 2. So 1 by 2 into adjoint 1 3 minus 4 minus 2 2 minus 2 1 minus 3 4. So this is the A inverse of the matrix. Now row reduced echelon form. Let us take an example for the matrix 2 1 4 3 3 2 6 9 1 1 2 6. This can be any m by n matrix. It can be a rectangular matrix. I am the first element of leading element of the matrix should be 1. So I am interchanging R1 by R3. So 1 1 2 6. I can multiply 1 by 2 with this matrix also. Since the element 1 is here, I am interchanging R1 and R3. 3 2 6 9 2 1 4 3. So the first element, first entry of this row should be 1, and in second row I should make this entry as 0. In order to make 3 as 0, in R2 I am replacing it as R2 minus 3R1. I am multiplying 3 with the first row and subtracting this. 3 minus 3 is 0, 2 minus 3 is minus 1, 6 minus 3 into 2 is 0, and 6 3s are 18, 9 minus 18 is minus 9. Similarly, R3 I am replacing as R3 minus 2R1. 2 minus 2 is 0, 1 minus 2 is minus 1, 4 minus 4 is 0, 6 2s are 12, 3 minus 12 is minus 9. I am adding the second, I have to make, in the next row, I have to make two elements as 0, 1, 1, 2, 6, 0, minus 1, 0, minus 9. Adding the R3 implies R3 plus R2. Adding the second and third row, sorry, subtracting the second row from third row, I'll get this matrix. And I have to make this should first element and the first entry is non-zero entry should be 1. So 1, 1, 2, 6. R2 is nothing but minus R2, 0, 1, 0, 9, 0, 0, 0, 0. This is the row reduced echelon form of A. If we can find the rank of a matrix using this by converting this into row reduced echelon form, hence rank of A is number of non-zero rows. Here we have number of non-zero row as 2. So rank of A is 2. Next, trace of a matrix. Trace is nothing but sum of diagonal elements of the matrix. Sum of if A, B, C. These elements may be anything. Trace is nothing but A plus B plus C. These are some of the properties. Trace of lambda A is nothing but lambda into trace of A. Trace of A plus B is trace of A plus trace of B. Trace of AB is nothing but trace of BA. Trace of A plus B is trace of A plus trace of B, whereas determinant of A plus B is not equal to determinant of A plus determinant of B. Here trace of AB is not equal to trace of A into trace of B, but in determinant of AB is equal to determinant of A into determinant of B. These two for trace and determinant we have to keep in mind these conditions. And trace of AB is nothing but trace of BA. Rank of a matrix. Rank is nothing but a number R is said to be a rank of an M by N matrix if every square submatrix of order R plus 1 or more is singular. That is, there exists at least one square submatrix of order R which is non-singular. If this is a 3 by 4 by 4 matrix, any submatrix, submatrix means we can delete any row or column and the submatrix should be of order R and this submatrix should be non-singular. If its determinant is not equal to 0 and the matrix is said to have rank R. Rank of a matrix is the order of the highest order non-singular square submatrix and it is denoted as row of A. Rank of A is less than or equal to minimum of M by N. Whereas in the previous example, we have taken a matrix, A is of a matrix 3 by 4 order. We got rank of A, that is rank of A as 2, which is less than 3, less than or equal to 3 and less than or equal to 4. And if rank of A is 0, then A is a null matrix. If rank of A is a null matrix, then rank of A is 0. If A is not a null matrix, then rank will be greater than or equal to 1. If A is a n by n non-singular matrix, then rank of A is n. If A is an n by n singular matrix, rank of A is less than n. That is, if determinant of A is not equal to 0, then the rank of matrix A will be n. If determinant of A is equal to 0, then the rank will be strictly less than n. If B is an R by R square submatrix of A such that determinant of B is not equal to 0, then the rank of A will be greater than or equal to R. Rank of a matrix does not change if it is subjected to elementary row or column operation. Even if we change any row and any column, rank will not change. Rank of A is equal to number of non-zero rows in row echelon form of A. Rank of A plus rank of B minus n is less than rank of AB, which is less than minimum of rank of A, rank of B. Rank of A comma B, AB is strictly less than or equal to minimum of rank of A comma rank of B. If a matrix is multiplied by a non-singular matrix, then the rank of given matrix does not alter. Nullity of a matrix. Nullity of a matrix is if a matrix is of rank R, m by n matrix, if matrix of m by n order, if it is of rank R, then the nullity of A will be number of columns minus rank. We have to find the rank of the following matrix. Here in this matrix, we have one is the leading element is 1, and the second row we are going to make this second row this element as 0. So R2 is nothing but R2 minus R1. 0, 4 minus 2 is 2, 2 minus 3 is minus 1, and R3 is nothing but R3 minus 2 R1. We'll get 0, 2 minus 1. These two are same. So 1, 2, 3, 0, 2 minus 1, 0, 0, 0, and number of non-zero rows is 2, hence rank is 2. But we can also see that the third order, second order minus, the third order minus, these two, if we take minor, it will vanish. So second order minus 1, 1, 3, 0 minus 1 is non-zero, so hence rank of A is 2. These are some of the exercises. I will send the PDF in the WhatsApp group. You can solve these exercises, exercise problems. So let us take the system of linear equations. A11 x1 plus A12 x2 plus A13 x3 equal to B1, and like this we can write this system of linear equations as matrix state space form, matrix form, where here A is the coefficients of the vectors x1, x2 and x3, and x is a column vector x1, x2 and x3. B is nothing but another column vector b1, b2, b3. Here A is called the coefficient matrix, x is the unknown vector, and B is the this is a column vector. The system of linear equations have a unique solution or infinitely many solution or no solution at all. No solution. If a system has a solution, then the system is said to be consistent. If a system does not have a solution, it is an inconsistent system. If B1, B2, B3 are all 0, then the system is called homogeneous system. Otherwise, it is a non-homogeneous system. So consistent, we are going to find the consistent and inconsistency of non-homogeneous and homogeneous systems by 3 ways: by using Cramer's rule, by finding the rank, and with the help of row reduction forms. Here, the first one using Cramer's rule. Let us take the non-homogeneous linear equations like this. Here, determinant del is nothing but the determinant of A, that is the coefficient matrices. This is denoted by del. Here, del x is nothing but substituting the x row with the elements d1, d2, d3. If we substitute a1, a2, a3 by d1, d2, d3, we can say it is del x. Substituting yth second row coefficients of y with d1, d2, d3, we will get del y. If we substitute coefficients of z with d1, d2, d3, we will get del z. If delta, that is determinant of the coefficient matrix, is not equal to 0, then the system of equation is said to be consistent and has unique solution. And solution is given by x equal to del x by x, y is equal to del y by del, z equal to del z by z. For example, let us assume let us take example 2x minus y equal to 5, x plus y is equal to 4. Here we can write 2 minus 1, 1, 1, x, y equal to 5, 4. Del is nothing but determinant of 2 minus 1, 1, 1, which is nothing but 2 minus of minus 1, 3, which is not equal to 0. Del x is replacing the first x coefficient of x with the scalars 5, 4, minus 1, 1, 5 minus of minus 4 is 9. Del y replacing the coefficient of y with scalars 5 and 4. 8 minus 5 is 3. So x is equal to del x by del, which is nothing but del x is 9 by 3 is 3, y is del y by del, which is nothing but 3 by 3 is 1. So the x equal to 3, y equal to 1 is the solution of this equation using Cramer's rule. If del is not equal to 0, here del is not equal to 0, then we are able to obtain the unique solution. If del is equal to 0 and at least any one of the determinant del y and del z is non-zero, then the given system of equation is inconsistent. If del is 0 and all the del x, del y, del z are 0, then the system is consistent with infinitely many solutions. For let us take the homogeneous system. Here d1, d2, d3 are all 0. Here del x, del y and del z are 0 because we are replacing del x with the coefficient of x with 0, 0, 0. And, hence del x is 0 and similarly del y and del z are 0. If so, we are relying based only on the determinant value, coefficient of determinant value. If del is not equal to 0, then the solution is x equal to y equal to z. This is called the trivial solution. If del is equal to 0, then the system of equation has infinitely many solutions and are called non-trivial solution. So, a homogeneous system is always consistent. Solution exists. Then by using matrix method. So here matrix AX, we can write the system of equations by AX equal to B. If determinant of A is not equal to 0, then A inverse exists. We can pre-multiply with A inverse. A inverse AX equal to A inverse B. A inverse A is identity, so X equal to A inverse B. We are able to find the solution X, that is A inverse B. For the same example, A is 2 minus 1, 1B, B is 5, 4. If it is a square, here it is not a square matrix. So here A is a square matrix. If finding the inverse and multiplying with B, we can find X is a solution space, that is 3 and 1. If A is non-singular, the determinant is not equal to A, we can multiply and we can find the solution like this. If determinant of A is not equal to 0, the system is consistent and has unique solution. If determinant of A is equal to 0, we have two conditions, either no solution or infinite number of solutions. For that, in order to find that, we have to find the adjoint of A into B. If adjoint of A into B is non-zero, then the system has no solution. If adjoint of A into B is 0, then the system is consistent and has infinitely many solutions. This is by matrix method. For a homogeneous system, here B is a 0 matrix. So AX will always be 0. If determinant of A is not 0, then the system has only trivial solution. That is x equal to 0, 0, 0. If determinant of A is 0, then we have infinitely many solutions. Next, by using rank method, we are taking the system of equations. We are taking the coefficient matrix Ax equal to B. Ax equal to B. We are augmenting the matrix A and B like this. That is coefficient A matrix with B1, B2, Bm. By reducing it into row reduced echelon form, we are finding the rank of A comma B. If rank of A comma B is equal to rank of A, then the system is consistent. If rank of AB is equal to rank of A, which is equal to n, it has unique solution. If it is less than n, it has infinite number of solution. So if rank of A equal to rank of B, it is consistent. If it is not, if it is not equal, then the system has no solution. If it is equal to the order, the number of columns of A, then unique solution. If it is less than the number of columns of A, then infinite number of solution. For in the case of homogeneous system, here rank of B is equal to 0, then AX equal to 0. It is always consistent. If AX for the system of equation AX is equal to 0, rank of rank of A into null matrix is equal to rank of A is equal to n. If this condition is satisfied, it has unique solution. If rank of A is less than n, it has infinite number of solutions. So these are some of the conclusions with homogeneous and non-homogeneous system. AX equal to B has a solution if B belongs to the column space. Column space. Okay, what is a column space? Column space is nothing but span of columns of A. That is, the columns of A should generate, the column should generate A. That is a column of, we are going to write columns of A as vectors in the field F and take all possible linear combinations. To form span. Column space is nothing but span of columns of A. So we are taking columns of A as vectors and taking all the possible linear combination, we will get the span. So if B belongs to column span of A, then A is equal to B has a solution. If rank of A is equal to rank of AB, it has a solution. And if B is linearly independent with columns of A, and a number of linearly independent vectors in S, and number of linearly independent vectors in S1. S1 is nothing but S union B. B is nothing but this matrix. If these are same, then A is equal to B has a solution. Just take a note of this. Dimension of S is equal to dimension of span of Sj. If these two dimension S and Sj dimension is same, we have a solution. And for homogeneous, keep note of it. If for homogeneous system, Ax equal to 0 has a non-trivial solution if kernel is not equal to 0 element, if rank of A is less than n, if nullity is greater than 1. Nullity is nothing but dimension minus rank. Nullity is nothing but dimension number of columns minus rank. If nullity is greater than or equal to 1, then the Ax equal to 0 has a non-trivial solution. And if A is not 1, if a kernel yesterday we saw if kernel is equal to identity, T is 1, 1. Here kernel is not equal to 0, hence T is not 1, 1. So A is not 1, 1. If m is less than n, number of equations is less than number of variables, then it has a non-trivial solution. That's all for today. We are going to solve some problems. Let D1 be the be determinant of A, B, C, X, Y, Z, P, Q, R. D2 is minus X, A minus B, Y minus B, Q, Z minus C, R. Option for first options D1 equal to D2, option B D1 equal to 2D2, option C D1 equal to minus D2, option D D1 2D1 is equal to D2. Let us take the determinant D2. I am going to shift the first row with the second row. So I will get, sorry, first I'm going to take the transpose. So if we take the transpose, I'll get minus x a minus b. Since determinant of a is equal to determinant of a transpose, I'm shifting this y minus b q z minus c r. And I'm taking minus from the first row. X minus y minus z a minus b minus c, and minus from the third row as well, so it will be plus. So p minus q minus r. I am interchanging these two rows. So by interchanging these two rows, I have to multiply by minus sign. So a minus b minus c, x minus y minus z, p minus q minus r. Taking minus from the second column and taking minus from the third column, I'll get minus into minus into minus into ABC, XYZ, PQR, which is nothing but minus D1. So I have obtained D2 is equal to minus D1. So this is the correct option. Next question. Let A, comma B be n by n matrices. Then trace of A square and B square is equal to A. Trace of A be the whole square, B trace of A B square A, C trace of A B the whole trace of A B square, D trace of B A B A. What we know, trace of A B is nothing but trace of B A. We already know this property. So from trace of A B C is equal to trace of B C, shifting this BC into A, and trace of shifting again C A into B. So it should be ABC, ABC, ABC. So it will be of cyclic form only. So we can write trace of A square B square is equal to trace of A into A, B into B, which is equal to trace of, I am going to shift this using 4 elements. So A, B, B, A. So ABC is equal to A, B, B. Trace of ABC equal to BCA. Using this property, I am shifting like this, which is nothing but trace of A, B square A. Hence, this option is correct. And in yesterday's assignment, you have got one some like diamond. What is the dimension of symmetric matrix of order n greater than or equal to 2, greater than 2 or greater than or equal to 2, with the first element 0 and trace equal to 0. So let us understand, let us assume for what, let us take, let us find the dimension of the symmetric matrix first. Here in symmetric matrix, here it will be A, B, C, B, D, F, A, B, C, D, E, here C, F. So this is a symmetric matrix. Here the elements are same. So dimension of a m by n matrix is m into n. Dimension of a n by n matrix is n square. Here the dimension of we have to find the dimension of the symmetric matrix. Number of elements is 1 plus 2 plus up to n. If it is a 4 by 4 matrix or 5 by 5 matrix, 1 plus 2 plus 3 plus up to n. Here we have sum is equal to 1 plus 2 plus 3. Here you in general for a matrix of order n, it will be n. Sum of first n element is n into n plus 1 by 2. So dimension of a symmetric matrix is n into n plus 1 by 2. Dimension of skew symmetric matrix. Skew symmetric matrix means here the entries will be 0 0 0, only 3 elements will be there. So 1 for skew symmetric matrix, 1 plus 2 plus up to n minus 1, 1 plus 2 up to n minus 1. Finding the first n minus 1 element, substituting n in the place of 1, n minus 1 into n by 2. So the dimension of skew symmetric matrix is n into n minus 1 by 2. We already know that any matrix can be uniquely written in the form of sum of symmetric and symmetric of and skew symmetric matrix. We know that dimension of for a n by n matrix, its dimension of A is n square. So dimension of a symmetric matrix is n square plus n by 2. Dimension of skew symmetric matrix is n square minus n by 2. So n square plus n square by 2 is nothing but n square. So this condition is also satisfied. So for symmetric matrix, it is n into n plus 1 by 2. Make a note of it. For skew symmetric matrix, n into n minus 1 by 2. So dimension of a n by n matrix is n square. If trace is equal to 0, a11, a1, sum of the elements, that is all the aii, summation of all ai equal to trace. We all know that sum of the diagonal elements is equal to trace. Let us take a n n, nth a n nth term. A n n can be written as minus of all the ai, summation of all ai, where I is less than or equal to n minus 1. I ranges from 1 to n minus 1. Sum of for a 3 by 3 matrix, if a11, this is any matrix, there may be some other elements. A22, there may be some other elements. Then a33 can be written as, we already know that a11 plus a22 plus a33, trace is equal to 0. A33 can be written as minus of a11 minus a22. Okay, minus a11 minus a22. So dimension of this matrix is n square minus 1. Except this term, all the matrices are coming. So dimension of the dimension of any matrix with the trace 0. Trace 0 is only one element is replaced. So n square minus 1. So we are going to prove the we are going to find the dimension of symmetric matrix of order n greater than 2 and with a11 and a trace is equal to 0. We know that dimension of a symmetric matrix is n into n square plus n into n plus 1 by 2. That is n square plus n by 2. Trace equal to 0 means nth element will be replaced, so minus 1. If a11 is equal to 0, if the first element is replaced by 0, then this will be removed, so again minus 1. So we can write n square plus n by 2 minus 2, which is nothing but n square plus n minus 4 by 2. So the dimension of a symmetric matrix of order n greater than 2 with a11 equal to 0 and trace equal to 0 is nothing but n square plus n minus 4 by 2. This is the correct option. There are some other examples also. Let A be a real upper triangular matrix. So A, B a real. Upper triangular matrix means only elements will be there. Let us take A, B, 0, C. It commutes with its transpose. If A is a matrix, real upper triangular matrix, it commutes with its transpose. A transpose equal to A transpose A. This is A matrix. A transpose is nothing but A, B, 0, C. A into A transpose is A, B, 0, C into A, B, 0, C. It's nothing but A, A square plus B square, BC, CB, C square. A transpose into A is A0, BC, A0, BC. A square, AB, AB, C square. C square plus B square. Since A transpose and A transpose A is equal to 0, these two matrices are same. So A square plus B square equal to A square, which implies B square is equal to 0, that is B is equal to 0. And AB is equal to BC. So this matrix, A matrix will be nothing but, since B is equal to 0, A 0, 0, C. This is a diagonal matrix, so option 2 is correct. Next, row reduced echelon form. I am shifting the second row with first row. 1, 2, 4, 0, 1, 3. Here they have, we can make this element as 0, 1. That is, in order to find this, R1 is R1 minus 2R2. So 1 minus 2, 1 minus 0 is 0, 2 minus 2 is 0, 4 minus 6 is minus 2, 0, 1, 3. The row reduced echelon form is this matrix. Here dimension of vector space of, here this is n by n matrix, question it is n by n matrix. N by n matrix with, when trace is 0 is n square minus 1. This is the correct option. Here number of non-zero rows is 2, so the rank of A is 2. For the determinant of the value of the determinant of this matrix. So I am multiplying, I am taking out 1 by A from this, 1 by A from first row. So A, B square, C square, A, B, C, A, B plus B, C. I am multiplying second row with B, so here I am dividing B, C square, A square, A, B, C, C, B plus A, B. Here A square, B square, multiplying this with C, I am taking out C, A, B, C, A, C plus B, C. I am taking A, B, C from the first column outside. So it will be B, C, C, A and A, B. I am taking again A, B, C from the second column, 1, 1, 1. And third column will be AB plus BC. AB plus BA. I am adding with the first column BC. CB plus AB plus CA. AC plus BC plus here AB. If I am taking AB plus BC plus CA outside, AB plus BC plus CA outside, I will get 1, 1, 1, 1, 1, 1, here BC, CA, AB. Determinant of this matrix is 0, hence the value of the determinant of this matrix is 0. This is the 2017 question. Here product of two orthogonal matrices is orthogonal and inverse of an orthogonal matrix is also an orthogonal matrix. Direct property they have asked in question. Here they have given a matrix. They have asked whether it is symmetric, Hermitian, unitary, or identity matrix. Symmetric means A is equal to A transpose. Hermitian means A is equal to A bar transpose. Unitary means A into A bar transpose equal to A bar transpose A is equal to identity. And it is clearly this is not an identity. We have to check all the three properties and we can find out from this. Yeah, the solution with the two unknowns with the determinant zero and any other determinants is not zero means with the two unknowns, then the solutions are dx and dy non-zero means the solution is inconsistent. Dx and dy is non-zero means solution is inconsistent. If A is a square matrix, we already know that A minus A transpose is a skew symmetric matrix. Direct property. If A is a 4 by 4 matrix, then determinant of minus A is, we are taking minus from the first row, and minus from the second row, minus from the third row, and again minus from the fourth row, we will get A itself, and minus 1 power 4 is nothing but 1, which is determinant of A itself. Comparatively for set exam, the questions will be direct and all the properties you have to read, and properties only they will ask us question. If phi is a real orthogonal matrix, determinant of phi is, we already see determinant of orthogonal matrix is plus or minus 1. So these are the direct questions. I'll send this PDF in the WhatsApp group, you can refer to this. And thank you. Tomorrow we'll see about eigenvalues and eigenvectors.
Thank you, ma'am. It's really wonderful session, ma'am. Our audience are very clear about this topic. Really, thank you, ma'am.
Thank you, sir.
So,
Thank you so much, sir.
whole commitment. You have spent many more time for this class. Really, thank you, ma'am.
Thank you so much, sir. Thank you so much.